Alright, the next section is section 14.2. We're going to talk about double integrals and volume. So here I've written out the definition for our double integral, and it uses the limit of a Riemann sum. So it says that if you have a function and it's defined on a closed bounded region R in your xy plane, then this is what we refer to here as our double integral of f over r, and r is our region in the xy plane. If the limit exists, then f is what we say integrable over r. So the volume formula is just like our iterated integral, but notice there's going to be some function here, f of xy, that is no longer just a 1 anymore. Next thing we have is Fubini's theorem, and it's just a very basic thing that ties together our double integral and our iterated integral. So it says that if r is a horizontal or vertically simple region and f is continuous on r, then the double integral is equal to the iterated integral. This next piece here is what I just mentioned. We're doing the same thing as before, except f of xy, our function, isn't equal to 1 anymore. So if you take a look at this double integral, let's take note of our bounds. So our inside integral is y, so y is bounded between x and 0, and x is bounded between 2 and 0. So what does that look like in terms of our graph? Well, the x is between 0 and 2, so I've got a vertical line right here. Y is between 0 and x, so y equals to 0 is a horizontal line, but y equals to x is a line with the slope of 1 crossing at the origin. So we've got this particular region. So let's integrate this, and we're going to have the integral from 0 to 2 of 1/3 x squared y cubed from 0 to x. And now this is going to get plugged in for y, so we're going to have 1/3 x to the 5th dx. So integrating now with respect to x, we have 1 over 18 x to the 6th from 0 to 2, which is going to be 64 over 18, or 32 over 9. So another example. Let's set up an integral for both orders of integration and use the most convenient one to evaluate. So here we have some region R, and our function is x e to the y. And I'm going to tell you R is bounded by y equals to 4 minus x, y equals to 0, and x equals to 0. So y equals to 4 minus x is a line with a y-intercept of 4 and a slope of -1. So this in here is our region R. So I'm also going to write this equation in terms of x, so that's x equals to 4 minus y. If we write this out as x e to the y dy dx, we need to think about our boundaries of x and y. So imagine we have a vertically simple region. We're going to sum those up from left to right, so 0 to 4, and our height of our rectangle on top is bounded by the line, so that's going to be 4 minus x, and on the bottom it's 0. Our other integral, if we write it out as x e to the y dx dy, we're going to have regions that are horizontal. So y is going to be bounded between 0 and 4, and the left-hand side of our rectangle is going to be 0, and the right-hand side of our rectangle is going to be the line, so 4 minus y. Let me go ahead and write in our bounds here, 0 to 4, 0 to 4 minus x, 0 to 4, and 0 to 4 minus y. Okay, so let's take a look and try to decide which one you want to use. So in this case, let's just try the second one. So when I integrate dx, I get a 1/2 x squared e to the y from 0 to 4 minus y dy. And I have 1/2 4 minus y e to the y dy. Oops, quantity squared. So this is looking like integration by parts, and it looks like I'm going to have to integrate it twice. So I'm thinking maybe let's try the other one. So this is 0 to 4. I'm going to integrate e to the y with respect to y, so that stays the same. 0 to 4 minus x dx. And I'm going to have x times e to the 4 minus x dx. And that's going to be integration by parts on the first part and just integrate the second one. So let's take a look. If we use integration by parts, we're going to have u being our x, du will be dx, e to the 4 minus x dx will be our dv. So the integral of that is going to be a negative e to the 4 minus x. So plugging everything in, we're going to have uv, so x e to the, x times negative e to the 4 minus x minus v du. So there's already a negative, so this is now going to become a positive, e to the 4 minus x dx. And I'm going to integrate that last part to be 1/2 x squared. So I have negative x e to the 4 minus x, I'm going to integrate again, minus e to the 4 minus x minus our 1/2 x squared, evaluated from 0 to 4. And plugging everything in, hopefully you guys will just trust me here, it's e to the 4th minus 13. One last example. Let's use a double integral to find the volume of the solid. So I'm going to go ahead and draw out a solid. And here we have our x, y, and z. So here I have my region R in my xy plane, and I'm going to have point up here crossing at 4, and this is actually going to be a paraboloid that reaches down this way. So if you kind of look, it actually has the equation 4 minus y squared, so it's kind of curving down. It's sort of a wedge-shaped piece. We're going to find the volume of this region. So the first thing I want us to do is to first identify the base region R on the xy plane. Now paying attention to how it looks like over here, let's see if we can translate that over. The intersection point here of these two lines is going to be 2, 2. So in that case, 2, 2 over here, and I've got this line and this one, but I hope you guys notice that I actually need this region on top. This is my region R. So now that I've sketched it out, I want us to identify the bounds. So taking a look at this, x is going to be bounded between 0 and 2, and our y is going to be bounded between, and be careful here, so on top we have the horizontal line, on the bottom we have the function x. So you can choose to write it this way, or we can choose to write it as y is between 0 and 2, and our x will be between 0 and y. So I want us to now write the double integral, and I'm going to do them one for each one. If I choose to write it out as 0 to 2 and x to 2, then we're going to put our function in here. We're going to take that function, 4 minus y squared, and write it in here, 4 minus y squared. Then this is going to be dy dx. Or we could write out the double integral from 0 to 2 and the integral from 0 to y, and we still use 4 minus y squared, but now we're going to write dx dy. Now evaluate either one. I'm going to choose to integrate the second one, so 0 to 2, because I'm going to have 4 minus y squared, then an x, from 0 to y. So now I have 4y minus y cubed dy, which is 2y squared minus 1/4 y to the 4th from 0 to 2. And that's going to give me 8 minus 16 over 4 is 4. So I have 4. That is the volume of this solid region. So this whole wedge-shaped region.